Hi guys, welcome to my lesson on completing the square. In this lesson, we're going to solve quadratic equations using the square root property, and we're going to solve quadratic equations by completing the square. So what is completing the square? That's our new vocabulary here. Completing the square is a method of solving quadratic equations by algebraically manipulating them so that one side of the equation is a perfect square. Okay, so you may recall that there are other ways to solve quadratic equations. We can use our zero product property, right, and factor them into maybe x plus m times x plus n equals 0. We can use our zero product property, but that's only if they're factorable. If your polynomial happens to be prime, then you've got to use some other method. And the other method you might have learned was the quadratic equation, where x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Of course, assuming that you had in standard form ax squared plus bx plus c equals 0. Okay, so you can use that. So why learn completing the square if we've got this alternate method for when our polynomials aren't factorable? Well, one reason is completing the square, just like the quadratic formula, can be used to solve every quadratic equation, regardless of whether it's prime or not. The other reason why it's important to study completing the square is you can use this when we're studying parabolas. We can write quadratic equations in what's called vertex form, where we can have some coordinates h comma k for our vertex, and we could write an equation for this in the form y equals x minus h squared plus k. Okay, and sometimes that's handy to be able to write that in a way that you can quickly pick off the coordinates of the vertex of the parabola. Likewise, if you're working with equations of circles, and this is a good lesson to review if you're going to be working with parabolas in vertex form or equations of circles. Okay, we have the coordinates of the center of our circle. We can call h comma k, and we can give this circle some radius r. And we have our formula for standard formula for the equation of a circle is x minus h squared plus y minus k squared equals r squared. And so hopefully you notice these binomials that are being squared. Okay, so if you were to FOIL those out, you would end up getting these perfect square trinomials. So it's good to know this trick, completing the square, so that you can manipulate these equations into the form you need so that you can conveniently work with equations of circles and equations of parabolas. All right, so could we solve this equation by using the square root property? And what do we mean by that? Well, I notice that this polynomial here on the left happens to be a perfect square. If you don't immediately recognize that, I'll demonstrate it to you in a second. You might also be saying, hold on, Mr. Rogers, you can't do that. We have to set this equal to 0. It's a quadratic. We've got to put it in this form, ax squared plus bx plus c equals 0, so we can factor it and use our zero product property. But if I did that, I might end up with a prime polynomial that couldn't be factored. Okay, so what's cool about completing the square and using the square root property to solve quadratic equations like this is that you can use it in cases where you can't factor. Okay, so for instance, I can factor this right now, even though this equation is not set equal to 0. And let's see what happens. I'm looking for two numbers that multiply to 49 and add to 14. And you probably are thinking, that sounds like 7. Okay, so you can factor this into x plus 7 times x plus 7 equals 64. And I know what you're thinking. nothing I can do with that because this is not set equal to 0, so I can't use my zero product property. But hold on. These binomials are identical. So we could rewrite this as x plus 7 squared equals 64, couldn't we? All right, and if we did that, now, because both of these binomial factors are identical, we can write it like this and take the square root of both sides. Because the square root of x plus 7 squared is just x plus 7. And the square root of 64 is plus or minus 8. Okay? So we're going to end up with two roots as we normally would. We subtract 7 from both sides. If we had, let's set this x plus 7 equal to positive 8 and x plus 7 equal to negative 8. These are our two possibilities. We'll subtract 7 from both sides. We get x equals 1. Subtract 7 from both sides here, and we get the other possible root is x equals negative 15. Good. All right, let's try another one like that. Hopefully you found that kind of interesting, the fact that we didn't necessarily have to set this equation equal to 0, especially if you find that you were starting out with a perfect square trinomial. And this one looks suspiciously like a perfect square. Notice some of the tips you're going to see are C is a perfect square, and A is equal to 1. Okay, or it can also happen sometimes when A is a perfect square itself. Okay, in this case, well, 1 is a perfect square, of course. And since A is equal to 1 here, we know it's going to be x and x. Remember our 6-piece puzzle. And we can factor this into two numbers. I need two numbers that multiply to 4 and add to negative 4. Okay, if they're going to add to negative 4, there's a negative involved somewhere, and if they're going to multiply to a positive, then they both must be negative. Okay, and that sounds like x minus 2 times x minus 2. Okay, all right, so you can see it was in fact a perfect square trinomial, so we can rewrite this as x minus 2 squared equals 8. Good, because now we can take the square root of both sides. Okay, and the square root of x minus 2 squared is conveniently x minus 2. And the square root of 8 is plus or minus the square root of 8. Okay, and the square root of 8 we can simplify to plus or minus the square root of. We can factor that into 4 times 2, which would give us 2 square roots of 2. Okay, so now we could set up our two conditions. X minus 2 could equal positive 2 square roots of 2, or x minus 2 could equal negative 2 square roots of 2. And we'll just add 2 to both sides to solve this guy. 2 plus 2 square roots of 2. And we can add 2 to both sides to solve this guy. And we get x equals 2 minus 2 square roots of 2. Good. All right, one more example using the square root property before we actually move on to completing the square. Let's take a look at this problem here. They want us to solve x squared minus 16x plus 64 equals 25. I'm looking at this guy, very suspicious that he's a perfect square trinomial. Let's see if we're right. Can we find two numbers that multiply to 64 that add to negative 16? Okay, and I can fill in my x's here because a is equal to 1. That's convenient. 8 times 8 is 64, and negative 8 plus negative 8 is negative 16. So this looks like x minus 8 times x minus 8, which I can rewrite as x minus 8 squared equals 25. Excellent. So we can use the square root property here, take the square root of both sides, and we get the square root of x minus 8 squared is just x minus 8. And the square root of 25 is plus or minus 5. Good. So we've got two conditions here. X minus 8 could equal 5, or x minus 8 could equal negative 5. Okay. We add 8 to both sides. One of our roots is x equals 13. We add 8 to both sides here. And our other root is x equals 3. Excellent. All right, one of the patterns you might have noticed in these last couple problems that we did is that if you have this written as ax squared plus bx plus c, you might have noticed that if you take half of b, which is -8, and you square it, you get c. Okay? Happens every time when you're dealing with a perfect square trinomial. If we take half of -4, -2, and we square it, we get 4. Okay? And likewise, in our other example, if we took half of 14, which is 7, and we square it, we get 49. So that's the key to completing the square. Now, we're going to learn these steps here. To complete the square for any quadratic expression of the form x squared plus bx, follow the steps below here. Step 1, find 1/2 of b, which is the coefficient of your x term. Okay, square 1/2 of b, and then add that result to x squared plus bx. Okay, now the problem is, of course, if you add it, then you have thrown the equation out of balance. You also have to add it to the other side, which I'll show you in some examples. It's not a big deal. You can, if you take b over 2 and you square it and you add it to this side, you just have to add it to the other side. When you do that, you're going to end up with the perfect square trinomial that you're looking for on the left side. And then if you need to, you can use that to solve using the square root property. Or you can simply take it and use it for some other purpose, like I alluded to earlier, working with vertex form or working with equations of circles. Let's take a look at some examples. Okay, here they want us to find the value of c that makes x squared plus 12x plus c a perfect square, and then write the trinomial as a perfect square. Okay, so what we're going to do is we're going to take b equals 12. And I encourage you to write these down until you get super comfortable with this. This will be really slick if you just write down b equals 12, and then write down b over 2 equals 6, and therefore b over 2 squared equals what? 36. And that's what c needs to be for this to be a perfect square trinomial. So let's write that out. X squared plus 12x plus 36 would make that a perfect square trinomial. And if you were to write that out in factored form, what would it look like? Now watch this little trick. If you want to go through this and do that, what two numbers multiply to 36 and add to 12, you can do that. But there's a shortcut here you may have noticed. Two numbers that multiply to 36 and add to 12, that's 6. X plus 6 times x plus 6. So we can write this as x plus 6 squared. Once you found b over 2, guess what? That is the number that automatically gets plugged in there and there. Okay, so you don't have to, once you get this written as a perfect square trinomial, you don't have to go through that thought process of factoring it. You've already got that number you're looking for, and you can just plug it in. And then you can write it as a perfect square like that. All right, so now the question is, can we actually use this idea to solve one of these quadratic equations? So let's go ahead and try this. We're going to solve this by completing the square. We're going to take b. It's 6. We're going to cut it in half. b over 2 equals 3. Don't forget that number. That's very important. I'm going to use it later. And then let's take b over 2 and square it. Well, that would be 9, right? So that's the number that I have to have right here for this to be a perfect square. Now, there's two ways you can approach this. And I find most students agree that the least confusing method is to start by doing this. The very first thing you want to do is clear out the c term entirely by subtracting it from both sides. Okay, and you'll see why in a second. Okay, equals -8. Because we agreed that c has to be 9 in order for this to be a perfect square. Now that there's nothing here, it's it's easier for me to think about. I can simply add 9 here to make this a perfect square trinomial. Problem is, I also have to add 9 to the other side. Okay, so I get x squared plus 6x plus 9 equals negative 8 plus 9 is 1. Good. And don't worry that this isn't a 0. I know we told you guys for the longest time, you got to set these equal to 0. You got to set them equal to 0. This is one case where you don't have to worry about that. Okay. So x squared plus 6x plus 9, if it is in fact a perfect square trinomial, how do we factor it? Okay, well, it's going to factor into, remember that number that we left over here, b over 2, x plus 3 times x plus 3, okay, which eventually you'll get so comfortable with these that you'll skip right to writing it as x plus 3 squared equals 1, okay? But it told us to solve the equation, right? Now that we've done this, we can go ahead and solve this equation using that square root property. Let's just take the square root of both sides. The square root of x plus 3 squared is conveniently x plus 3, and the square root of 1 is plus or minus 1. So we've got two conditions here we can solve. X plus 3 could equal 1, or x plus 3 could equal negative 1. Good. Let's subtract 3 from both sides here to get x equals negative 2, and let's subtract 3 from both sides here to get x equals negative 4. Good. Those are your two roots solved by completing the square. All right, that's all well and good, Mr. Rogers, but what if a doesn't equal 1? What do you do then? Okay, not a problem. Just make it 1. Well, how do we make a 1? Mr. Rogers, you can't just change that to a 1. No, we're going to use the rules of math. We're going to obey the laws of math. And in order to make a 1 here, I would divide both sides of this equation by what? This is divided by 3. Okay, and what we're going to be left with is x squared minus 2/3 x minus 1/3 equals 0, because 0 divided by 3 is 0. Okay, now let's clear out this c term here, so it'll be easier for us to think about. Let's go ahead and just clear that out by adding 1/3 to both sides. So I'm left with x squared minus 2/3 x, and I like to just leave a space here so my mind can think about, hey, I need to get something in there. I'll leave a space for a c term, and equals 1/3. Good. Okay, same thing here. Don't be intimidated just because it is a negative fraction. No big deal. B equals negative 2/3. So what's b over 2? Well, b over 2 then would be negative 1/3. Remember this is your magic number. Okay, this will go into your factored trinomial when you're done. And then what is b over 2 squared going to be? Well, negative 1/3 squared is going to be positive 1/9, right? So that's what I need right there for this to be a perfect square trinomial. I'm going to go ahead and add 1/9 to this side. As long as I add 1/9 to this side. All right, I'm going to clean this up and rewrite it over here. I get x squared minus 2/3 x plus 1/9 is going to equal, I'm going to add 1/9 to 3/9 and get 4/9. Good. Okay. Well, we said this is a perfect square trinomial. All I've got to do is take my magic number and put it in there. X minus 1/3 squared equals 4/9. Okay. It's as simple as that. If you ever doubt this, or you want to test it or check to make sure you've done it right, you can write this as x minus 1/3 times x minus 1/3 and FOIL it back out and confirm that you do in fact get this trinomial. It'll work every time if you're doing it right. But eventually you'll get to this shortcut where you'll say, I'm just going to take the square root of both sides now, and I get x minus 1/3 equals the square root of 4/9. It's going to be plus or minus the square root of 4/9. And you might recognize your quotient property here will come in handy. Get plus or minus the square root of, well, this is equal to the square root of 4 over the square root of 9, which turns out to be 2/3. Gotta watch your math teacher there, right? So we can solve this by pulling out our two possibilities. X minus 1/3 equals positive 2/3, or x minus 1/3 equals negative 2/3. And we can add a third to both sides. And we get one of our roots is x equals 1, and we can add a third to both sides over here. And we get our other root is x equals negative 1/3. Okay, so is it a problem if a doesn't equal 1? No, not a big deal. Just start by getting rid of that a, or turning it into 1 by dividing the entire equation by a. You may end up with some fractions, but that's not a big deal. We can work with fractions, right? And you go through the same steps that we did to complete the square when we had integers. No big deal. All right, one more problem like that. Solve 2x squared plus 11x plus 15 equals 0 by completing the square. Well, a is 2. We've got to fix that. We want to make a 1. So let's just go ahead and divide the whole thing by 2. We'll get x squared plus 11 halves x plus 15 halves equals 0. Okay. I would like to clear out this c term. I think it's going to make it cleaner by subtracting 15 halves from both sides. So we get x squared plus 11 halves x equals negative 15 halves. Okay, so let's go ahead and say there's our b. B is 11 halves. What's half of b? B over 2 is 11/4. Okay, dividing fractions in half is fun like that. All you have to do is double the denominator. Hopefully you guys knew that trick. B over 2 is 11/4. Therefore, b over 2 squared is going to be 121/16, right? So c has to be 121/16 in order for us to make this a perfect square trinomial. Let's add 121/16 to this side, as long as we also add 121/16 to this side. Okay, so I'm going to go ahead and rewrite this, clean it up a bit. Get x squared plus 11 halves x plus 121/16 equals negative 15 halves happens to be negative 120/16. So this is going to be negative 120/16 plus a 16th, or plus 121/16 leaves us with positive 1/16. Okay, if you want to write that out, you can. This here is just negative 120/16 if you multiply both top and bottom by 8. So when we add these together, we're going to be left with positive 1/16. Okay. Oh, I forgot to circle our magic number. Our magic number is b over 2, right? So all we have to do is pop that into x plus 11/4 squared equals 1/16. And now we can solve this using the square root property. We take the square root of both sides. We're left with x plus 11/4 equals plus or minus the square root of 1/16. Okay, which would be the square root of 1 over the square root of 16. The square root of 1 is 1, and the square root of 16 is 4. Okay, so now I can set up my two possibilities. X plus 11/4 equals positive 1/4, or x plus 11/4 could equal negative 1/4. Good. Let's subtract 11/4 from both sides. Okay, we get x equals negative 10/4, right? Which simplifies to negative 5 halves. Okay, or we could subtract 11/4 from both sides here in our other condition and get x equals negative 12/4, which simplifies to negative 3. Okay, so there are our two solutions. Okay. All right, guys, thanks for watching. I hope you found that helpful in learning some tricks. One more trick for solving quadratic equations, but don't forget this is a trick you're also going to use when you're working with equations of circles and when you're working with equations of parabolas in vertex form. Okay, so I'm hoping you'll remember this trick as more than just a way, an alternate way to solve quadratic equations. It's also a way to manipulate expressions so that you can work them into equations of circles or parabolas. Thanks for watching, guys.